from what Louise has said, you'll be aware that robotics has been used in manufacturing for over 40 years. Actually, its application in maintenance, which is what we're going to talk about tonight, people like me are interested in, is actually quite rare. But our fleets hopefully will grow in the next 20 years, continue to do so, and our land available for new facilities is actually quite hard to come by, particularly in places where we maintain a lot of our trains, like in central London or on the outskirts of central London, and other major cities. Our working age populations probably will decline in number. And when I talk to people like my sons and say, do you want to get up at 9 o'clock at night and go out and put fuel in the train or clean it overnight in the rain, they're not that interested in that as a job prospect. And I think we will actually struggle in future to find people to do some of these tasks. But actually rail vehicles, when you look at them, lend themselves to kind of production line type facilities. So you can see on my illustration from a car manufacturing facility, that actually those cars are moving along on rails. So actually robots do actually hold for us, particularly in vehicle maintenance. They're quite attractive, and we're maybe actually quite well suited to it as an industry. So where are their applications? There's stuff that is dull, stuff that gets us dirty, stuff that gets us, it's quite difficult to do and maybe dangerous. For example, work on high voltage equipment, working in fairly hazardous chemicals, and stuff that we do very frequently. If we do stuff frequently and we can get a robot to do it, that's probably got the best business case. So, for example, I work for Chiltern Railways. We fuel our trains every 2 to 3 days. It's a sort of task that would lend itself to being used to a robot doing. Cleaning, we clean our trains every night, inside and outside. We top up fluids, we replace brake blocks and brake pads every night. And then on the electric trains, we replace shoe gear and pantographs. I don't envy people who have to get up on pantographs to replace the carbons. It's whilst we create and set up, we spend a lot of time setting up safe systems of work. There's surely a place or a position for robots to do that better for us. So over the past few years, there have been a number of academic studies and work sponsored in the first place by RSSB, and there was some work by the University of Birmingham, the University of Brunel University, who did a lot of work with me on application of robots to fluids, and Cranfield initially did quite a bit of work on how to clean train fronts. And some of that has been taken forward and is being developed into industrial products, particularly with a company called GBR Rail. But we are, as an industry, struggling to create the business environment that takes us from academic studies into real life applications of robots in the workplace and on our railway. But tonight, we're going to hear from Cranfield. Professor Andrew Starr is going to talk to us about the work he's been doing with NetRail on the approach to using robots on on infrastructure maintenance. And then Professor Gareth Tucker is going to talk to us about the work that Huddersfield are doing in their robotics laboratory on rail vehicle maintenance. There is a third research group in the country at the Strathclyde University in Glasgow, who are also doing quite a bit of work on robotics in rolling stock. So we as an industry, we've gathered a bit of a research base in this, and we now need to try and develop the ideas and take them forward to actual railway trials. So the next speaker is going to be Professor Gareth Tucker, and he's reasonably well known in the industry, and I'm going to hand over to Gareth.
Hi everyone, just share my slides. Hopefully you can see that okay. So I'm Gareth Tucker, I work at the Institute of Railway Research in the University of Huddersfield. I'm going to tell you a bit about our work on the use of robotics for train maintenance. This is part of its long title, Smart Rolling Stock Maintenance Research Facility, which is an ERDF funded project. So this is just a bit of a background. We spend a lot of money in this country maintaining trains every year. So the cost of maintaining the whole GB passenger fleet is nearly £250 million a year. So anything we can do, to save a small percentage of that, that's going to add up to be big numbers. And it's costs more to maintain a train through its life than it does to buy it in the first place. So the whole life cycle cost, obviously it varies by fleet type, but on average 40% of the life cycle cost of a train is on maintaining it during its life. And it's a long asset life. We think, as Simon alluded to, that the passenger fleet is going to keep growing. Obviously, COVID made a big impact on passenger travel. There's still predictions that things are going to rise, maybe more slower than they would have before COVID, with predictions saying 20% over the next 20 years. Obviously, if petrol and diesel keep going up like they are, then it is going to drive more people back to public transport, and it might go back to our previous imagination of what the growth might be. In Simon's introduction, he also alluded to other industries using a lot of what we call smart technologies, which includes robotics and other things, data analysis to inform decision making, optimize scheduling and planning, and augmented reality, and I'll mention them a little bit, as well as the robotics. A lot of you might be familiar with this concept of Industry 4.0, which is getting a bit of a buzzword recently. It's merely focusing on manufacturing, but the idea is we're trying to take those concepts and apply them into a rail maintenance environment. So in the picture there, Industry 1.0, effectively, that's the Industrial Revolution. Industry 2.0, that's like James T. Ford, early 20th century manufacturing lines. Industry 3.0 is bringing some automation in computers, and where modern manufacturing now is this Industry 4.0. And that top right is a picture of a car, a car factory, and there's a lot going on there. And then there's a nice, quiet, serene train, they're modern and clean in the bottom right. Some of you might be familiar with the Railway Technical Strategy, which is the industry level sort of aspirations or plans for development. I think there'll be a chance for me to share these slides later on. So if you get them and you're interested, you can click on the link there for a website about that. One of what they call the functional priorities in that plan, this plan's delivered, led by RSSB and RDG, is reliable and easy to maintain. It's a picture of a train in the icon there, but it is actually applicable to train and infrastructure. So things gone slightly out of order. So this is like a route map for that reliable and easy to maintain area. I've just kind of highlighted some areas there. And you can see that column I'm highlighting, vision for 2025, so 3 years from now, is do we use more condition-based maintenance and inspection? Yep, great. Widespread use of robotics and AI to identify and in some case rectify asset faults, which seems a bit ambitious 3 years from now. And if we really do want to do that, obviously we've got to spend a lot of research and development time in order to do the implementation. Obviously in the real world, if it doesn't happen in 3 years' time, it happens in 5 years, it happens in 10 years, that's great too. But this is just showing there is some industry level kind of aspiration to do something with robotics, either for trains or track or whatever we think. This then is just trying to show a high level overview of this perfect future world where everything is modern and all integrated together. This isn't my pitch, I can't claim credit. It's from BCG Analytics, and there's a link to web page on there as well. But you can sort of get the overall idea here that all our trains have got a lot of RCM on, and modern trains are already starting to do that. So will be connected back to some sort of center, a data center that's going to do a lot of analysis, know all the movements of all the trains, know how far each train has gone every day, where every train is across the network, plan maintenance in the most efficient, optimal way. And inside the depot, you'll have robots doing some of the work, not all the work. You'll have a digitally enabled workforce, so every staff member will, on a mobile phone, have a little app that's telling them the work they're going to do that day. That can link in with what the robot's doing. They can put in their results of their own manual or visual inspections. Also, an idea, maybe some stuff can happen during traffic hours when the train's in service, potentially. And that's just sort of showing the wider picture. So the project I'm working on is the Smart Rolling Stock Maintenance Research Facility. That middle picture in the bottom is our new lab, and I'll talk about that in a bit more detail. So it's not just about robotics. I'm talking about the robotics element today. We've also got what we're calling the virtual depot, which is it's not a 3D model of a depot, it's a workflow model, which we use for work optimization and planning, RCM data processing and development, which we're using for the main element, that is trying to make better use of existing data that's already collected from trains to actually directly inform the maintenance, and the augmented reality, which we think is a way of helping to either train staff or use as an aid during repetitive tasks so people don't forget things. And as an aspiration, at some point, maybe we're going to try and integrate that as a way of controlling the robots and calling programs on the robots. That's down the line. So this is a research project. We're just starting out. We're trying to see what's possible. But we're starting from a solid base of some work that's already been done. They're the objectives of the Smart Rolling Stock Maintenance Research Facility. This is all the sort of things you might expect. We want maintenance to be more efficient, more effective, reduce train risk of in-service failures, and try and make things more efficient overall. So you can read them off there. You don't need me to read every bullet point. We've got a project steering group, of which Simon is one of the members representing the train operators. We're also starting to work with some other research partners, and got the things up there. The project team at the university, I've just listed the names on the bottom right there. My colleague, Dr. Hamid Reza Faham, he's the one who's actually doing all the work with the robots. I can't claim the credit, I'm kind of managing the project. So just before we get on, just try to sort of set the scene of what we're talking about. A lot of my friends and colleagues, I tell them, I'm doing research into robotics for train maintenance. They think I'm talking about like these little robot men in the top left. And, that's science fiction, maybe one day, but probably not in my career that's going to happen. We're talking about industrial robots, a range of which are there in the middle, top middle. That's the sort of thing we're talking about. And then just on this slide, there's a few examples of things that are already out there being used or starting to be used. So the bottom left is the on the MTR system in Singapore. It's a cleaning robot, similar to some of you might even have robot vacuum cleaners in your house. It's like the same sort of thing, but an industrial powered version. Top right is the Siemens automated wheel set Traversal. So it's maybe not what you might imagine a robot to be, but it's a piece of automation that's moving those wheel sets around the factory. Bottom right is Chinese CRRC inspection robot. So you can see you're looking there in a pit, and that traverses up and down. It's on wheels, moves up and down in the pit, and it's got a camera on it that does some inspection. And that's a development system, but it's obviously quite close to being ready. You can see it's there in a real depot. It's a very clean depot, so I don't know if that's a research facility or an actual operational depot. Fluids, topping up of fluids or emptying CET tanks is something that Simon already mentioned, and there's been a prototype system developed to start showing some of the capabilities or possibilities of that, which by Brunel University on the left. There's also a system in development in Germany with DB, and there's a company, they called it Acceptance, trying to be a clever little pun like aqua and septic tank, so it fills up the water and empties the CET tanks. Again, that's a prototype, it's not an in-service system, and you can see they've done a simulation of it as well in a robot simulation program. So these are sort of areas we think where robotics and automation might be applied. Cleaning, which I've mentioned. Obviously, we've already got automatic train washers. It's not trying to replace that. It's trying to for the outside of trains, but it might be doing the train front end, or on DMUs especially trying to do the underframe cleaning. Servicing, we mentioned fueling, sanding, water CET emptying. Inspection, I think, is a big element of it, and that was mentioned in the RTS as well, or possibly replacement of some parts, probably smaller components like your brake pads, carbon strips, which Simon mentioned, any bolts that are missing. You know, maybe a robot can find a missing bolt and then replace it. This is a survey we've done across about 60-ish different responders. Bottom right is showing where the people that respond to the survey works, or the type of organisation they worked in. So the more than half from, well, around half from the train operating companies, who are the people that might be using this type of thing. And the main response of what do you think would be useful to apply. Obviously, when we go away and prove what's possible, we'll see if that still remains the same. So it's not straightforward trying to put robotics into a train depot. Then these are the sorts of challenges I think we need to start addressing. Obviously, in a manufacturing production line, everything is brand new. Everything is moving through. It's exactly the same place every time. Each robot is doing a specific task, and everything is exactly where it should be every time it gets to its station. In a train depot, you've got a train coming in. It's got a target point of where it's going to stop, but there's some tolerance within that, and any robotic system needs to be able to adjust for the exact stopping position of the train. Any components that have worn out, obviously the height of a train changes over time as the wheels wear, and the robots need to be able to adjust for that. Robots also probably going to have to do multiple tasks rather than just one single repetitive task. Also, there's challenges around how we introduce, if we're using industrial robots, they need to be segregated from people. We need to work out how we might do that. And the business case obviously is a big challenge. We need to be able to demonstrate there is a solid business case if people are going to go away and spend money up front on a lot of robotics equipment. So this is our new lab. Just got this finished 2 weeks ago. And the idea helped us do a proof of concept of what is possible with robotics for train maintenance. It would have been great to get a much bigger room and have a whole vehicle in here, but this is the space the university were able to give me. So it's an 8 meter long pit. So the idea is representing a section of a train depot. We've got a bogie in there. In there, which are KR50s, 50 kilogram payload, 2.5 meter reach. In the pit, we've got a what's called a collaborative robots, and these ones can work with people in the same environment. And that's a UR10, which also moves up and down on a little track underneath. Just another view of the same lab. That's showing in the pit with that UR robot I mentioned on its own little track. This is a very short video done for commissioning, just showing the robots moving around. That one's got our vision system on it. So it's used the vision system to find a block, which is now going to pick up, then takes it over. That just movement shows you how quickly a industrial robot can move. It's going to pass it to the other block, the other robot in the pit. That robot in the pit now is just going to move along the pit, raise the block up. Obviously, this is just showing what's possible and showing that the robots can all connect to each other. We actually need to start using them to do some realistic maintenance tasks. At the back there, we've got our tool changer. So end effectors for industrial robots are expensive. So if you can share them between multiple robots, you can save a lot of money. And that's what we've done here. You can see the robot closest to us has put the end effector back on the tool changer. Further away robot now is picking it up. And then it's going to use that gripper to pick up the block from small UR robot in the pit. So I'll just briefly explain a few other parts of the facility. So that's our CEng's vision system, which is mounted on one of the robots. This is just going to show an example of the system doing a particular inspection. So here, robots moving the camera to inspect the bolts on the axle end cap. So it's found the end caps, taken a photo. Just kind of click through this a bit because I don't want to use up too much time. It's moving around. This is in a slow mode, reduced speed mode, because there's someone in the cell with it taking the video. It's now moving there. It's moving the camera. I'll just click through. It's just going to then take a photo of that end cap on that axle. This is now just showing how that looks in our vision system. So this particular bogie, which is a 321 bogie, this end cap's got 5 bolts. And the vision system has got 5 areas. Looking at each bolt, just quickly go back. So each one of those 5 in this picture is also the earthing strap bolt, which is separate and not included in this analysis at the moment. So there's a condition of each bolt. In this picture, all 5 bolts are in the OK. Bolt 2 is in the not good status, and you can see the bolts missing. This picture, bolt 4 is in the not good status. And just looking a bit closer, if you zoom in, what's happened there, you can see that the witness mark for the torque tightening is not lined up with the witness mark on the cap. So there's a problem with that bolt that is not correct, it's shaken loose. So this is a nice automated way of inspecting those bolts. This is a laser line scanner we've got on the other robot. This is just going to show a quick video, and then it's scanning the top of a wheel profile. So wheel profile is normally measured, with a mini prof, and that's measured in a position that's tangential to the surface. Again, if you don't know exactly where your wheel is parked relative to your robots, you need to scan along the top of it to find the highest point, which is where the wheel profile will be taken. That's just showing it's a blue scanner and measured rail profile we could get. I've just shown it taken from the top of the wheel. In this example, where in a real depot, obviously there'd be the car body in the way, but we'd find a point where we could get into do the measurement. So that's a very quick whistle-stop tour through our new lab, the things we want to try out. We're at the start of the journey. We've got ideas of the things we want to try. We've got some industrial partners. Quite happy to talk to anyone else that wants to get involved, and you can get in touch with me to do that. So just in conclusion, we think there is a high level of interest in this area, but at the moment, we don't know exactly what is the best way to apply robotics into train depots. There has been some initial work done, but we think there needs to be a lot more work to demonstrate what is possible and investigate exactly how to implement this sort of stuff in the real world. So what we're doing now, obviously we just got that lab and we need to learn out how to use it, what we can do. We're trying to identify some specific procedures that we want to try. I showed the laser scanner there, taking a 2D line profile. The next step is to make 3D surface shape, because we know the coordinates of the robot as we move it around the cell. We can therefore turn our 2D images or 2D measured shapes into a 3D shape, which will help us with different types of inspection. We've done that initial study of the vision system, which I showed with the bolt ends, and we want to carry on developing that. The next thing, we're also now already in procurement for a third end effector for industrial robots, which is a nut runner. I call it an electrical torque wrench, but robot people call them nut runners. So you think obviously unbolting things and bolting things on is one major thing we want to start doing. And the other element is we're not necessarily just interested in the depot. I think bogie overhaul is another big option for use of automation. And maybe that's more similar to a factory environment. And it could possibly be the one way that we could get the robots into the railway environment is in the bogie overhaul facilities, where you've got workstations with more repetitive tasks and things moving through to different workstations, more like a factory. And that's all I was going to tell you, is a quick rush through the topic area. I'd just like to quickly mention we have got an event on the 10th of May, which is our joint Northwest region and Northeast region event hosted in Huddersfield. And if any of you want to come to that, which is an in-person event, you can do a tour of all our labs, including this facility, on the same day if you turn up early. Thank you, everyone. Simon, I don't know if we're doing questions or we do that at the end.
I think we'll do some questions at the end if we can, Gareth. That might be better.
Right.
Thank you, Gareth. That was useful and an interesting summary of what you're doing at Huddersfield. Good to see the laboratory and what's proposed. So our next speaker is Professor Andrew Starr. Andrew is a professor in robotics at Cranfield University, and he's been exploring their use in rail infrastructure maintenance. So Andrew, I'll hand over to you if that's okay.
Thanks very much, and good evening, everyone. So thanks to Gareth for a very interesting start to the evening, and in this presentation I'm going to go on and talk about the way in which robots are used on the infrastructure as opposed to vehicles. So firstly, some credits to my team. As Gareth has pointed out, you don't do this alone, you do it with quite a lot of people, and there's a lot of different skills involved. So we've got people who are good at making practical stuff. We've got programmers, we've got people in instrumentation, navigation, simulation, and so on. So it is certainly a team-based activity. Firstly, a little bit about Cranfield and my centre. So principally, we work in areas of whole life support for high value assets, and there's a range of different companies we work with in aerospace, defense, transport, manufacturing. And about the only bit of the whole life that we don't really do much in is recycling and end of use. But we do a lot of work with life extension and during the life of the assets, looking at maintenance in terms of decision making. There's a lot of new digital tools for artificial intelligence and remote presence and so on. We work in health systems for both machine health, but also some human health as well. And we also develop courses for an industrial base as well. So Cranfield is all postgraduate, so we don't have any undergraduates. We focus on postgraduate courses, and we've got at any one time typically about 40 PhDs within the centre as well. So in this session, I'm going to talk about some of the infrastructure applications, and I'll dwell a little on how they differ from what Gareth's just talked about, because some of the robot devices and concepts and some of the sensing is very similar, but we do have some rather unique problems for infrastructure. We need to think about how the fixed and the mobile robotic devices work together, and importantly, we've got to get them to places. So location is important. It's got to be repeatable, and it's got to work everywhere, and navigation for getting people and equipment to the right place is important. Then we'll have a look at what type of measurement devices we need out in the field, and what could be done in terms of payloads for actuation. And then finally, I'll look at some of the test environments that we're working with. So firstly, about the challenges. There's a very wide range of jobs out in the field and in infrastructure. And when you think about what people and devices are doing out in the field, they're often getting ready to make either repairs or major replacements, installation, and that can be either spot activities, like, for example, small-scale tamping or replacement of components. But it can also be in preparation for much wider survey for example, track replacement or switches and crossings. So as a consequence, the range of equipment goes from something that could be very light, for example, inspection or measurement tools, which could be really lightweight trolleys or handheld equipment, all the way through to the heaviest thing that a person can operate, and then right through to machine operated equipment. And really we're interested in anything which is smaller than the big yellow plant. So tamping and track replacement is perhaps out of scope, but anything smaller than that, where there are moving plant road rail vehicles, that gets into scope. So some of the other hazards which are really important for the people involved are that there's plant moving about, and often it's not separated from the people. And it could be in very remote places. It's inviting to think that junctions and stations are very accessible, but often the places are extremely remote, and road access is required to get there. And the weather is not always kind, and it's common to have to work in the dark as well, with appropriate lighting and some of the problems that goes with that. So today, there's a relatively low level of automation. So if you think about, for example, track tamping, then there is a level of automation in the big equipment for the pressure, the number of cycles in the tamping times, but there's always human supervision. And indeed, the nature of working with automated equipment on the railway is that broadly the autonomous equipment is not allowed except under very, very controlled conditions. So you can think about, for example, Docklands Light Railway has vehicles which are under automatic operation, but they're supervised, and a few airports have some automatic transition, and there are level crossings, but there's not much else that is completely automated. So one of the key areas is to think about how that is to be done in terms of the regulations required. And we're not trying to get this done by the middle of next year. It might take 10 years or 20 years before the level of complete autonomy is achieved. But in the meantime, during that 20 years, we can be confident that we will need some kind of collaborative behavior with people working close to machines. So you can see one of those on the right-hand side, and a guy's working with quite a heavy machine here, but he is at a controlled distance from it. It's been working towards him as it's laid those sleepers, and it's also got somebody in control of that machine. It is not an automatic machine doing that. So in order to build up to large-scale demonstrations, we're building up through the technology readiness levels or the rail readiness levels, through laboratories, then equipment that's like a railway, but it's a big step to a real railway. And we are working with some laboratory environments, which I'll show you in a minute, but also on some heritage railways, which are indeed live in that they do carry passengers. So there's a lot of rules that they follow that the main railway does. So we started out at a small scale to look at some of the technologies associated with fixed and mobile manipulators. So what you see here is a 5-inch gauge vehicle, which was done as quite a quick demonstration. It was built in about 3 months for one of the European projects, and it immediately gives rise to some observations. So you see on the back of this vehicle, there's a small laboratory robot, a benchtop robot, and it's quite accurate. That will do 3D printing in polymer while it's on the benchtop. When it's on the vehicle, it's got all kinds of problems about precision and uncertainty. So this vehicle, like other railway vehicles, has got flanged and coned wheels. So when it moves around on the railway, well, it has some freedom of movement from side to side, and because of the coning, it also means that it can move up and down a little bit. So the robot's not ready for that. The robot requires finer precision to be able to do what we like it to do. So that might sound perfectly obvious. It is once you know it. The benefit of hindsight is wonderful. But what we were able to do with this vehicle is to demonstrate a number of key things. Firstly, a physical demonstrator. Some of you may have seen this at a show already. It's been to a few exhibitions before the pandemic. And it also enables us to demonstrate some systems integration. So the vehicle has a controller. In order to control a system, you have to decide what's in charge. Is it the vehicle or is it the robot? And you also need the drive systems to work in a way that is not the same as a locomotive, for example. Locomotives generally are there for pulling things along and driving them at a given power and just occasionally at a given speed, but they're not intended for location. So this thing is retrofitted with encoders for location, for example. The integration of the systems is quite important because it needs to be able to get sensing in and out, and also steps of the control to turn it into a robot rather than the conventional vehicle. And then really important on top of this is a layer of command and control that simulates a real job going to a vehicle, the vehicle accepting that job, and then giving feedback to say that it's done that job back to the overall command and control system for job control. So we use a simulation of Network Rail's ellipse system for job control and simulate all the steps that are demonstrated as the vehicle searches and repairs. So in Interþemaat 2, within the Shift to Rail program, we moved up to a larger platform for inspection and repair. And again, the command and control is important here. And not only is there the yellow machine in this country, but we also work with Strukton, Chalmers University in Europe, one in Sweden, one in Netherlands, and we work with command and control processes that will talk to them remotely for their part of the demonstration. This is a proprietary autonomous guided vehicle, and it can drive in remote control models. So the guy on the right hand side here is driving it to site along the road. Then it can be adapted onto a trolley, and this is a bespoke trolley built for the vehicle, which has got rollers allowing the thing to on track and off track. If you ever talk to any of the plant manufacturers and lease companies, they'll tell you that one of the biggest challenges they have is on and off tracking. And we can confirm that. It is fundamentally hard to do, to get from ground level onto a vehicle on top of the rails. So that requires some manual intervention to get it up there. It climbs up on ramps, but it does it under manual control. Once the vehicle is on the trolley and on the railway, then the navigation task is very simple, because essentially it goes backwards and forwards. But instead of going perhaps hundreds of meters from an access point off the back of a trailer and onto the railway, then the task for perhaps an overnight inspection is anticipated to be 20 to 30 kilometers under its own power. So this is part of a range of demonstrations to try to get this at a higher scale, and also further up the technology readiness levels in terms of demonstrating the technology. So this continues to be operated within the robotic operating system framework. So what we're trying to create here is an agnostic framework, so that this vehicle and any other vehicles in the family can be programmed to talk to the command and control system, and can have their own detailed programs developed, but in a way which, if this changes to another platform, is easily switchable. And the future for the robot operating system and its latter versions is really quite exciting in terms of unmanned ground vehicles and drone type inspections, mobile robotics, because it's being quite widely used by the research community, and also a number of different railway administrations as well. So we've been talking, for example, to the French Railways, SNCF, about their application of ROS Industrial. So about the sensing, well, these vehicles can be loaded up with a lot of sensing for, firstly, location and navigation. So to know where it is, the vehicle is fitted with a global navigation satellite system, GPS, and we've also been using it with a real-time kinematics add-on. So GPS generally is good for about 8 meters. With RTK, it works to about 20 millimeters, which is fantastic, as long as you're within range of its base station. And this is a fundamental issue for the railway, because you don't really want a base station every 200 meters or so. That would create a high cost and then a maintenance legacy to drive this. So we're very interested in ways of simplifying location. GPS and the signaling system offer a degree of location for a vehicle on the railway, but there are places that you can't really get a very good registration of location, and those include tunnels. They include Faraday cages, like station roofs, and wherever there's a lot of metal work, basically, it really disrupts the GPS because it needs line of sight to many satellites. So what else have we got on board? Well, for situational awareness, there's LiDAR, which is a laser scanner approach, and the top right image has that output. And what you can't quite see, because I've deliberately taken the animation out of this because it's been done over a Zoom session. I was a bit worried about bandwidth. But some of the objects that you can see around the periphery are clearly walls and other obstructions, but there's also a person here. And this is very important for some of the collaborative work, because we need to get the robot to detect when it's got obstructions or people working nearby. Then there's some of the payload. So there's cameras all over this vehicle. So the top one here is the onboard vehicle mounted forward-facing camera that can be turned around almost 360 degrees. And there's also another one in this position where the hand is here. And you can see that being used in the lower right image, where it's looking at a QR code on the rail. And the robot is able to manipulate itself so that it can give multiple views onto different parts of the railway, which is quite a handy way of not only observing, but also simulating types of observation on the railway and actuation. The other one on the list that I didn't mention is when we haven't got access to GPS, then there's also an inertial measurement unit, IMU, which works by acceleration, gravitational attraction, and it is useful for when there's no GPS. It does have the problem that there's continuous drift. IMUs have that problem, but on the other hand, they can be corrected with fixed observations as well. So they're part of the solution, as are encoders for rotations of the wheel. Now, of course, a rotation of the wheel on a railway wheel gives very, very low slip. But with this particular application, we've got rubber tires, and when they're on the ground, they have a relatively high slip rate, which needs to be monitored. And there's even some slip between the rubber tires and the rollers here as well. The combination of all those things goes together in software, and here you can see lower right a visualization in RViz, which is part of the ROS suite. Gazebo and RViz are used for programming visualization in this context, and you can see here what the robot sees. That is, it sees a number of cones of information, which are then stitched together to give it a sight of its environment. And in this case, it's an indoor environment, and you can see that there's a pillar, there's a box, another pillar in the distance, and some structure behind it, which it has identified. And it's also got some obstructions we know are there, but it hasn't yet identified because it hasn't been close enough to measure. So more about localization and navigation. This is a requirement because the nature of the purpose of getting out to the site is to be able to measure things and actuate things with a good degree of precision and repeatability. So, for example, there's no point going out to replace a clip on a track or look for a crack in a weld if we are looking at the wrong crack in the wrong weld, for example. So the repeatability of that remains really important, because there are some locations on the railway that really we only know by, for example, it's a signal, the length of the signal section. Vehicles and drivers don't really know their location that accurately, and the repeatability of the combination of systems based on simple things like encoders for rotations of wheels is subject to the starting point, the size of the wheel and its relative wear, and any slippage that's taken place. So this localization is quite a complex problem. So I mentioned before that GPS would appear to be a brilliant solution, but without RTK, it's only good for about plus or minus 8 meters. It's deliberately fuzzed up by its owners, the Americans. You need in the order of 7 to 11 satellites to get a decent fix on it. And there are plenty of locations. For example, think about a cutting or an area with large buildings around the railway. Then what you actually see is a narrow part of the sky called a canyon in this context. And those give pretty poor visibility of the sky. Even some dense vegetation. And it's estimated that between 10 and 20% of the railway has no GPS fix. So we're working on a range of different approaches to improve that with different types of references. The railway has plenty of references, things like signal posts, overhead electric masts, and in the next generation we're going to look at techniques for getting a lot more information from the track itself and the patterns that are recognizable on the track. There is already a commercial solution for this. Once the position is available, then mapping is a key issue. And many of you will have seen some really vast improvements in mapping for railway-based and other network-based approaches. So different users have different contexts. Some are interested in route settings, some are interested in planning, some are interested in timetabling. But in the context of maintenance of the asset, then we're very interested in track defects and where they are, and what the history is, and what causes it, whether it's drainage or damage or interaction with the dynamics. So one of the key things is to be able to do this navigation with a minimum of human intervention. Human beings can spot a lot, and they can do a lot to do with training, but the ultimate aim is to be able to do this with zero human intervention. So off track and in a test environment, we can allow this vehicle to go and use a technique called simultaneous location mapping, SLAM, and it trains itself and observes its own location. As I showed you on RViz before, you've got to do several circuits before you get the full information, but it learns as it goes. And we're also very interested to get the vehicle to respond to obstacles, and also those things around the vehicle might be people. And if they're alongside this vehicle on the railway, then they're not really an obstacle. They're just working in collaboration. But if a human being steps in front of the vehicle, even if that is against procedure, we need the localization using LiDAR and depth cameras to immediately identify that there is some body moving here, and therefore to slow down or stop. And this is in fact common with a lot of collaborative robotics approaches in the manufacturing environment and in hospital environments as well today. So bringing together perception, localization, planning and control is run-of-the-mill for the robot operating system. Moving on to some of the actuation, we've been asked to demonstrate a number of different payloads on the vehicle. And one of the initial observations is that, and you may have spotted it, that the Universal Robot 10 robot arm is okay if the Warthog robot is on the ground, but it's actually too short to do much on the railway. So it can pick up plenty of good pictures, but here you can see we've got on the left hand side, this is a Sperry stick with, no, I reserve judgment on whether that's a Sperry. Somebody in the audience will correct me. It's an ultrasonic device which is hand operated for rolling along the track looking for cracks. We borrowed this one from British Steel, which is why I'm not sure if it's Sperry. It has a sensor in the little trolley at the bottom. There's water for coupling it to the rail. And here what we've done is a proper Heath Robinson lash up to get the Warthog's trolley to propel the stick along the railway. And what you can't quite see, but I'll show you in a moment, is that we've got a number of seeded faults built into this piece of rail here. So on the left, on the concrete sleepers, we've got a continuous panel of track which happens to have a couple of welds in, but other than that, it's in good condition. The shorter piece on the right-hand side has been modified in our workshops with some standard network rail test indications. And for the interest of expediency, you can see that we have fish plates here, but we don't have the bolt holes through. Because it's quicker and they need adjusting fast when you're doing demonstrations like this. And this vehicle has done a series of iterative tests to detect these seeded faults here. On the right-hand side, you can see a robot-mounted infrared camera on a piece of track, and this rail is modified in a different way. It's got a set of test features which are machined onto the bottom of the rail, and that's using active infrared to detect damage which you can't see from the top. And ultrasonics is pretty good for the rail head, but it's not much good for the foot. So this is an approach to get the infrared camera deployed using automated technology to scan the rail. This is an imperfect experiment. You can see that we can get at some of the foot of the rail very well, but it's much harder to get in around the chair. That is a distinct issue with that type of technology. But the image below, which has a fault made in the bottom of the rail, that is not taken from the underside. That is active infrared going right through the rail's flange on the lower side of the rail. So the instrument is flashing that from the top and detecting the fault which is underneath the rail. So I mentioned a bit about the test environments. So middle of last year, we had this delivered on site. Cranfield's an unusual university. We are the only university in the UK to have its own airfield. And as a consequence, we have space. If you're in the middle of town, then you're always short of space. And that is a bit of a challenge. So you can see that we've got space here. We'll probably build up another 2 or 3 panels and possibly an S&C panel in this as well. A close-up here of the faults which have been put in for seeded faults. So there's some holes drilled right through, which are detected from the railhead. And then these faults and cuts here are drilled into the rail end, and are drilled at an angle to simulate tash ovals, a particular type of Crrc feature, which is of great interest to automate. And then bottom right, you see where we're going testing in April, which is a heritage railway at the Northampton and Lamport Railway. And we will be doing longer distances here for the first time over S&C, and also over a variety of legacy track. So you can see some of it is concrete sleepered, there's flat bottom, there's the older bullhead rail, there's wooden sleepers as well. So it gives us a number of different opportunities there. And last but not least, this is the next generation for automation. This has just arrived in February, and this is going to be adapted for automation. At the moment, this is a manual electric push trolley. So the manual controller plugs in either end, and the driver drives it always away from him or herself. It'll carry up to a ton, and versions of this are available with seats on, and can handle heavy equipment and so on. This is a proper approved product for the railway, and our job is to adapt this for command and control using ROS2 in this case, the latest version of the robot operating system, and we will need a completely new control and sensing suite for this, which is designed for the next phase. And in particular, we're interested in developing this with the UK supply chain, because the Warthog, as good as it is actually made by a Canadian manufacturer, and they've been much harder to work with than colleagues in the UK. So finally, a bit about the future. Please pay no attention to the shape of this vehicle. It could be any shape, but I wanted to try to identify where some of the big changes would be to remote operate or retrofit some of the vehicles that are already available for the network. And a lot of that is about sensing. So, for example, vision and other situational awareness sensing, drive-by-wire actuation. So the retrofit package we're designing for the balance trolley is critical to that. It's real-time processing and sensor fusion. All the rest of the darker blue boxes already exist in product development, and there's a lot of excitement in the supply chain about getting more automation into these areas. Remote control is one of the first things to do, radio remote, and then increasing amounts of driver assistance. So finally, in conclusion, the key driver is probably the idea of less people, less boots on the ballast. But the railway needs a continuing and expensive, rigorous maintenance programme. Lots of operators across Europe have told us their need for survey work, for close-up flexible inspection, so that they can plan their work ready for precision interventions, whether that's with people or machines. And then we think that some of the key work in the future is going to be about regulations, specialist regulations for the railway, and some about people doing collaboration, but also some about independent vehicles on the railway. There's a key piece of work to do about how you get an object onto the railway, because trains go from depot to station, pick people up, do jobs, take freight, go back to the depot again. Robots aren't going to do that. They might just appear on the railway, and currently that is frowned upon. Things which just appear on the railway are kind of a problem for the signaller. And there's also more work to be done about actuation, because as I mentioned at the beginning, the heavyweight stuff is dealt with by the big yellow trains, but light to mid-weight tools that are perhaps on the limit of what human beings can operate up to what a medium weight road rail vehicle can operate. Those are going to be very interesting for flexible interventions. Which brings me to a close. Thank you very much for listening.
Thank you, Professor Starr. That was very interesting and very heartening almost to hear the progress that's been made on the infrastructure. I feel that you're probably nearer getting stuff in use than perhaps we are in some of the maintenance aspects on the vehicles. Louise, do you want to?
Yeah, I was going to say thank you to all three of you. That's been very interesting and eye-opening, and certainly some aspects that I'd not even contemplated as either a problem or an opportunity. So that's a good reason to listen to lectures like this. So we've got some time for some Q&A. If you'd like to either drop your question in the chat box, which you can activate by bringing your mouse towards the bottom, pressing the chat bubble, and then a menu type thing should appear on the right hand side. Just type in the space that says type message here. And I would genuinely invite people to submit whatever questions they want, because the only dumb question is the one that doesn't get asked, as far as I'm concerned. There'll be something that you know somebody doesn't know about, and it could well be one of our three speakers, so don't be afraid to ask. And equally, if it's just something that's helping your curiosity, then that's a good reason to ask it as well. So please do go ahead and ask. We've got a couple of questions already come in. First one, I think, is probably aimed at yourself, Andrew.
Yeah.
Which is about water being used as a couplant for ultrasonic inspection. Does it use much water, or is there some form of reclamation?
The short answer to that is no, not much water. And you could see on the walking stick device that it carries a few litres with it. We do find that the amount that splashes about during any one test is, you'd wish to be outdoors with it, shall we say. It would need mopping up indoors, but no, it's not a huge amount. And it only needs a valve to turn it on and off during the test cycle. It doesn't matter if the sensor runs dry, but it won't give a good signal if there isn't a couplant there. In the laboratory, we'd use a kind of gel, so it wouldn't run away.
Okay, hopefully that answers your question, Anil. I've got a sort of chair's prerogative kind of question, which I'd like to try and get off my chest sort of sooner rather than later, and hopefully it'll provoke some debate, which is around forecasting the future, which I know is always an imperfect science. But if knowing what you know now compared with, say, what you knew a year ago or even perhaps slightly longer ago, where would you, Simon, you're a train operator, Andrew, Gareth, you're not in the train operators world, but you're seeing it from the opposite end of the spectrum. Where do you think the best opportunity is, and why?
Well, what has moved quite quickly, I think, is the understanding the needs of the operators. And for infrastructure, that is often the national authorities, like, for example, Network Rail or Deutsche Bundesbahn, passing contracts on to their civil engineers who are also using a supply chain. And this is kind of linked to something that Kevin Blacktop's put on the chat, which is what would unlock further adoption of the technology. Well, it's getting the participants to talk to each other, which, from my point of view, is relatively easy. We have been able to engage with operators, with maintainers, with civil engineers who share quite well. However, the contracting to get jobs done can be a bit obstructive, because it might all work to the lowest price and highest performance. So we do continue to need these research environments, either in the UK through, say, UKRI or Innovate, or through the European programme Shift to Rail, and the new one, European Rail Joint Undertaking, because you got to get people playing ball to make it happen.
Okay, Gareth, what's your perspective on the biggest opportunity?
I think for train maintenance, any sort of procurement of big new fleets that also come with a depot, like HS2, for example, you've got the chance there to straight away design the train that's suitable for being maintained automatically and build the depot, which is already a big up cost, to have robots straight away. And to just design your whole maintenance system to include automation, robotics, predictive maintenance, everything. Retrofitting and stuff into depots is, it's not impossible, but it's more of a challenge. And yeah, I think that's the big thing. And straight away, I think already we can show inspection is a useful thing to do. Changing small parts. But really, we need to work on the business case to prove this is a useful thing to do. Otherwise, no one's ever going to be able to buy any of this equipment, which is expensive up front.
How about you, Simon? What's your perspective?
I kind of sit alongside Gareth. I think as a nation or a country, we probably need to, on our next new big fleets, perhaps incentivize or dare people to bid something that is slightly different, which will include some robotic maintenance. And that may well encourage the supply chain to start investing in this for vehicles. Unfortunately, it's too easy to bid what we know now.
Yeah.
Or how we've always done it.
Yeah, the railway is understandably very conservative in this.
Yeah.
And you can see why we might do that, but we also end up with some solutions. Well, on track, we've got some solutions that date back to about 1870. And they work. There's nothing wrong with them as such, but it takes some bravery to specify something different. And there's no doubt features on vehicles that also have some of the same problem.
I do think with train procurements, all these supply and maintain contracts, they should be encouraging this kind of thing. Like you can cost your upfront investment into improved maintenance over a longer period of time, especially if the maintain period is longer. And measuring stuff better is reducing risk. Having more repeatable maintenance, again, it's reducing risk, and that's how we think about it.
Yes, and having run a maintenance depot for 4 years and seen some of the challenges in actually sort of distributing staff over the times you need them with the right skill sets at the right point in time, and then again, peaks when you think peak of workload's going to appear, and it doesn't. It comes when you've got the sort of lesser staff quantity on board. The better we can take out the stuff which the humans really don't do very well, and leave them to do the stuff they really do very well, better than machines can do. That to me, as an engineering director, would be hugely appealing. I think you're absolutely right. The opportunity to put it alongside a new fleet procurement has got to be sort of one of these staringly obvious kind of moments. I think there's an interesting question. Another interesting question to follow on is then, just how big is big? Because we have a horrible habit in this country of buying 20 or 30 trains at a go. Is that enough? Probably not. Don't know. Anyway, that topic for another time.
Yeah.
Okay, we've got some more questions coming in. Kevin, you picked up Kevin's question, Andrew. So a question from Richard Flint. Do we think that we can get to a point where ultrasonic axle testing is automated? Ho, ho, ho. Who wants to grab that one by the horns?
Well, from the ultrasonic point of view, absolutely yes. And it's already automated in some other industries. There's bits of nuclear power stations that you can't get to, so there's crawling robots for that. I'll hand over to Gareth for comments on getting it in the depot.
Well, I think absolutely, and I think that's probably one of towards the top of the list of things we might try, especially when you've got a takeoff and axle end caps, and remember to put everything back together better. I think, and again, do we really need to do as much ultrasonic axle testing as we do at the moment? This is a separate question. Like, I think we introduce more risk of train failure by doing it because of these human factors things than we do of actually doing it. It's like axles don't actually fail that often. But that's a separate conversation, I suppose.
Well, yeah, as I said, go and see the freight guys and you'll learn something. Because my EWS colleagues, certainly on the American designer wagons, we gave up doing axle testing 25 years ago. So there's definitely an opportunity there.
That's because the Americans build so much redundancy into things, Louise.
There's a whole design philosophy that goes along with it, Andy. I'll absolutely grant you, but definitely agree with Gareth's point about introducing more risk when you take things apart and put them back together again. Number of axle incidents that back that up.
True for lots of other transport situations as well. That is the root of reliability-centered maintenance for aircraft, because it's had the same problem. Quite so.
I should say, if anybody wants to ask their question in person rather than putting it in the chat, then you're more than welcome to do so. And Stephen's waving his hand, so go ahead, Stephen. You better unmute yourself. Well done.
Thank you. Yeah, thanks. I've been waiting patiently. Thanks, everyone. I've got a few questions. So, Louise, shut me up when my time's done, please. But I think some of we're currently involved in some sort of artificial intelligence and data gathering exercises in freight at present. And some of the questions that keep coming up are entirely practical. We're looking at quite futuristic systems, to use simplistic language. You're at the pinnacle of robotic rail research. But these things are going to be commonplace. I've got absolutely no doubt that we're going to be seeing, whether it be cobots or robotic arms, whether in assembly maintenance facilities going forward within 5 years. I mean, technology is moving that quickly. Some of the practical questions that we're encountering now are relating to 30-year maintenance contracts. Let's take HS2 vehicles as an example. There'll be a 30-year maintenance contract on that. There'll be robotics demanded as part of that contract. Who owns the software on the robotics? Who's going to maintain the software for 30 years? What happens when Robot 10.3 software becomes obsolete and the owner of that software says it is no longer in existence? I was at a seminar recently where someone started laughing about Windows 98 still being used in some depots, but they're working on Freight Wagon 1975 in terms of the braking system on it. So the sort of practical issues that probably aren't part of your concern right now, but in terms of the ownership of that intellectual property, that's the first question I've got. The second one is, who are these programmers? How do you see the future, and how are we going to change the education system? The people coming through your establishments are effectively programmers. So in our factory environment, the best people to program a PLC generally are our CNC operators, because they understand that level of code and the simplicity. And if we're programming a cobot for a CNC machine, we often find that the CNC programmer is much better than our master's engineer. So do you see mechanical engineers, electrical engineers, or software engineers being the driving force behind robotic introductions and maintenance of the robotic systems going forwards? So I think, well, I'll shut up and hand it over and get your opinions, please, if you've considered those things.
Okay, well, may I start? I think the the problem is an important one. It's important that you raise it, but I don't think it's any more important than some of the tooling and instrumentation that is already being used, because that's already got programs in it, and some of that already has obsolescence issues and support issues. So, for example, if you wanted to do engine diagnostics for a diesel locomotive, well, you're going to have to use some software tools. It doesn't just come with a spanner to fix it anymore. And the mainstream robots. So Gareth demonstrated some popular suppliers' robots. They're the orange ones, so that tells you who they're likely to be, unless they've been repainted. And they support their technology worldwide with a lot of experts who have designed it, programmed it, manufactured it, and they support them worldwide. And there's also an onward supply chain as well for support of industrial machines like that. So I'm not very worried about that. The latest developments actually are rather like you described, in that, as I mentioned at the beginning of my presentation, I can't do it with one person who's a programmer. That's no good. I need people who can make stuff and screw it together and wire stuff up. If we're going to lash on a new sensor, we need to understand, what does it do? Physically, how do we, for example, get a 3D camera to detect a human being? Well, we've got to get a tape measure out and work out how far away will it detect. We've got to physically screw it on the box. We've got to wire it up with some power supplies. So we're getting really multi-skilled people to develop such things. And I think that is also something that I see in the supply chain that we're seeing with our conversations with ClearPath and Bants, for example.
My observation, I'm not a great knowledge in this area, but when I have talked to robot manufacturers, obviously this is not a problem that's unique to the railway. And they, as Professor Starr said, they do generally sell the robot with a long-term support package that and maintenance, etc. In terms of programmers, I think that will be and people who develop the software, that is a challenge, probably particularly for the UK. We're not great at developing people with those skills, apart from computer games. We seem to be quite good at that.
Perhaps we should go down that route and borrow some of those guys. I think there's possibly also some other areas of development that we might also draw upon. So a couple of years ago, I was working with some guys from UCL who have a very fast processing 3D object recognition from LiDAR approach. So we don't have to do everything from first principles. We can draw upon other sectors and other developments to get better quicker. We just have to get out more. Good question, Stephen.
I think probably, new graduates coming into the industry working in fleet engineers, they're the sort of people we should be training up to be able to do the programming of robots for the depot environment. It's people that understand the things the robot needs to do. And on a basic level, a lot of robot programming is not as complicated as we might imagine. It's just moving things around in 3D space and coordinates, and that side of things isn't going to change with new software releases. It's the clever stuff on top that we need the specialists to come in for. And there's a lot of like robot integration companies all around the country I didn't buy those robots from the manufacturers. I bought them from a reseller, and that reseller, they've got people, and I bought them from a Huddersfield company, Olympus Technologies. And I think the same would be true. Like a depot would either buy them from a reseller or they'd buy them with the support package, and they'd have these, these software engineers or robot programmers that would be there on hand working with them. As a whole industry, I think, need to be thinking about the skills side of things.
Yeah, we do, definitely.
It's in data analysis and all of this. But there's no reason why engineering graduates can't learn how to do this more computer sciencey stuff, I think.
Mm-hmm. Well, the trains are a set of computers on wheels, so
yeah, exactly.
Absolutely. Yeah. Yeah, it's
Okay.
a multi-skilled world, isn't it?
Absolutely, absolutely, and a completely different one than the one I started in. Okay, so I've got a couple of questions more, and then I think we need to draw stumps. So from Rich Gray, how do we think smaller scale robotic inspections might hopefully compare performance-wise compared with existing? Oh, sorry, I'll start that again, Rich, my apologies. How do you think smaller scale robotic inspections might compare performance-wise compared to existing larger operations, such as the new measurement train or other forms of in-service condition monitoring on trains?
Yeah, good question. Well, the NMT, of course, goes at full tilt, 125 miles an hour. You'll be pleased to know I'm not planning to send one of these devices along the railway at 125 miles an hour. So we are interested at the moment in slower scale and much greater precision, because NMT is good for certain things. So, for example, plain line pattern recognition gives a very high resolution of the point, and usually it's got GPS. But I've been on NMT, and we were going through Watford Tunnel, and I can tell you, you don't see any satellites as you go through Watford Tunnel, and it takes about 30 seconds to lock on again as it comes out of the tunnel. So you are dependent at those points on the encoders and IMU on board. So getting a greater resolution is something that is particularly important. And also the large, fast plant really doesn't come back and check. So the ability to iterate and to come back and look at a particular fault or a query several times before it moves on, that's also of great interest. So it does fit in rather than replace. It's filling some gaps.
Okay, okay. Right, and then the last one from Richard Flint. For rail vehicle maintenance, should we be thinking about robotics for inspection tasks can be implemented at stabling locations such that the need for depot visits is reduced? Is this considered in current research?
Yeah, absolutely it is. And I think that's a real opportunity. The different challenges are there that the robot's more likely to be outside, so they need to have IP66 rating, and if you are using vision and it's raining, you need to account for that. So that's certainly something we want to look into. Okay.
IP rating's easy though, and it's robots were designed for tough situations, so we haven't been very worried about that. The Warthog is rated for wading.
Okay, great. Well, yeah, obviously the infrastructure robot is outside naturally, isn't it? So yeah.
Well, funnily enough, the railways do turn into rivers from time to time.
Yes.
Rotherham Station a couple of weeks ago.
Yeah, and
years, I'm told.
That's a very valuable point, because although we've been looking at things on rails and sleepers mainly, I think there's a great deal of interest for getting off the railway and looking at drainage, and in the 6 foot and in the cess, there's all kinds of mischief going on.
Yes,
so to be able to do that with an unmanned ground vehicle would also be very interesting.
Indeed. Right. Thank you very much, gentlemen. I think, Stephen, are you going to do the vote of thanks for us?
Yeah, with pleasure. With pleasure. Thanks, Louise. Gents, Andrew, Simon, Gareth, thanks ever so much for this evening and your time talking at the North East Centre. There are a lot more questions I'd like to ask. I'm impressed with the technology, obviously. It's great for us to see the future in such capable hands as is demonstrated to us tonight. I'd like to know when you're just going to jump a step and go past moonlanders and go straight to UAVs fitted with gimbals, laser scanners, X-rays, and just fly these things, around, and then you don't have the problem of touching anyone's track. your GPS and your radar has to be good. But you know, realistically, you know, Futurama's with us, and it's a matter of time before we have things buzzing through tunnels. Hopefully not at the same time as vehicles, but we will have, you know, God knows what buzzing around our heads, our infrastructure, our depots. In I feel the not too distant future. Excuse the old kitty cat. So apologies. Yeah, it's been really interesting. I think we've had an audience of about 50 people here tonight. We had 2 screens of 5 by 25. I counted up. So there was a lot of interest in the research that you're doing, in the projects you're working on. It's really good to see rolling stock infrastructure operators, you know, working so closely together. And you could just see the number of logos on your opening slides. The amount of collaboration happening across the industry is so significant. You know, you have the support, I think, of pretty much every kind of body within the industry. So, you know, we wish you very well. We thank you so much for the presentation you've given us tonight. You've probably inspired quite a few people to go and think about the future. And that's why we gather. So I'd like everyone to sort of give a round of applause, but it doesn't kind of work so well on Zoom. So my cat and I will give you a round of applause. So thank you very much, gentlemen.
Very good. Thank you, Stephen.
That's okay.
So a little bit of an advert. Next week, March 23rd, please do come along for our Future of Rail competition. 2 young guys competing, very different backgrounds, 1 apprentice, 1 graduate engineer. And we need to encourage the apprentices very strongly to progress. They are our future, as well as the graduates, so mustn't forget them. And they do appreciate your support, and you probably will learn something as a consequence of listening to them, because they're doing the kind of stuff like this, actually, that us old fogies and silver-haired amongst us actually can't tackle because we're not up to it anymore. So do come along and learn something, and ask a dumb question, ask any question you like, because they're tomorrow's engineers. And then on April the 5th, as I said earlier, our freight colleagues at WH Davis will be giving us the benefit of their time, and hopefully a video-based tour of their facility if we've managed to get that fixed up. So that could be very interesting and an eye-opener for anybody that's not had anything to do with freight. Do keep an eye on our programme. I put the link earlier on in the chat. If you just search for IMechE near you, Railway Northeastern, you will find out a list of our events and a list of the people that arrange all these things for you. So you can rant, you can rave at us, or you can make some positive suggestions, whichever you prefer to do. Otherwise, I'll bid you all, I would say a safe journey home, but I know most of us are already at home. But anyway, safe coming months, and avoid getting the plague. And we'll see you as soon as we possibly can in person, ideally in May in Huddersfield, but if not, later on. So take care. Good night, everybody, and thank you very much.
Thanks, everyone.
Thank you.
Thanks again, Louise, Gareth, Andrew, Simon.
Thanks, Louise.
You're welcome, Andrew. Thank you.
See you soon.
Bye.